Okay, good morning class. Right, so can you hear me clearly? Can you hear me clearly? Okay. So let's say if you cannot hear me clearly or the line is not okay, can you please tell me? Alright. So today we continue. Okay, we continue to with our lesson. Okay. Oops, sorry. Alright. Can you give me like a minute? Okay. I want to open the commit with my phone. Okay. So let's continue with our lesson. So only one student come from 4M. Okay. Okay, so this one I think already discussed, okay, in our previous lesson. Okay. So this one we already know that the Newton's universal gravitation of law already stated that the force of the gravitation is actually directly proportional to the product of mass of the product of two mass, right? And another one, the force of gravitation is inversely proportional with the radius, with the r square. Okay, so then you can derive the formula. From that, we can derive the formula G m1 m2. Okay, divide by r square. Okay, and we already learned how to use this formula. Okay, all right. So what is the relationship? Okay, so the larger the mass, the larger the gravitational force, and also the next part is the larger the distance between the bodies, right? The smaller the gravitational force. Okay. So next we move on to the solve problems, okay, involving Newton's universal law of gravitation for objects on Earth's surface, okay, the Earth and the Earth and the satellite, okay, and the Earth also and with the Sun. Okay, so what is the gravitational force on the man-made satellite, okay, before it launched, okay? So can you try to calculate this one first? Okay, try to count the force, the gravitational force for the man-made satellite. Okay, between the man-made satellite and also the Earth. Okay, please find the force and give me the answer. Okay, by using the formula G m1 m2, okay, divide by r square. Okay, so the value of G is 6.67 times 10 power of negative 11, right? Okay, and then the mass of the Earth is wait, okay, that one already given to you. The mass of the Earth is 5.97 times 10 power of 24, and the radius also already given. Okay, be careful with the R. Okay, because actually the R is the radius of the Earth, right? But now you have to calculate the distance, right? The force between the Earth satellite and the Earth. So means there's still some distance here. Okay, the radius is only from here to here. Okay, and the distance between the Earth and satellite, okay, is 4.22 times 10 power of 7, okay, for this one, and the radius for Earth is 6.37 times 10 power of 6. Okay, so for R, okay, now you have to be careful for for the R. Okay, so which one you have to take? Whether the radius of the Earth or between the distance between the Earth's surface and the main satellite. Okay, using the formula here. Okay, so M1 maybe you can take the mass of the Earth. Okay, M2 maybe you can take the mass of the man-made satellite. Okay. Wait, I check the value for G first. Is it correct? 6.67. That's correct. You can move. So anyone, you got the answer already? So, still the answer? Why is the R here? You have only to take the radius of the Earth, or you have to add the radius of the Earth and also the distance between the Earth and the satellite. $202.47 Newton. 202.47 Newton. Okay. Other any other answer from 202.47 Newton? Two point zero 2.56. Okay, so let's see which one is the correct one. So any other people want to try to give the answer? So M1, M2, R square, right? Okay, so 6.67. Okay. Times 10 power negative 11, and then you multiply with the mass of the Earth times 10 power of 24. Then you have to multiply with the mass of the man-made satellite 1.2 times 10 power of 3, and then you have to divide with the R. So R is actually, okay, so before this we only learn that the object is on the surface of the Earth, right? Let's say an object, let's say a pupil, okay, anything that is on the Earth, on the surface of the Earth. So that's why we only take the radius of the Earth. So let's say this is you, right? So we only take the radius of the Earth because you are still you are still in the surface of the Earth. But let's say if your satellite, you know that satellite is at the outer space, so means there are still a distance, okay, some distance. So let's say this is satellite. So the distance you cannot take the radius of the Earth. You have to take the R. This is from the R, and then you have to add one more, the distance of the Earth to the satellite. So they already give you the distance between the Earth and the satellite is 4.22 times 10 power of 7, right? So the R is what? The R is actually, okay, the R is actually 6.37 times 10 power of 6. Okay, you have to add with the distance between the Earth and the satellite. So add 4.22 times 10 power of 7. Okay, so this is the value of R. Okay, because before this, all the calculation that we calculate, okay, the question before this is all the object is on the surface of on the Earth. Okay, but this one is satellite, so they are at the space, so there must be a more distance, right? So it's further, right? So there's still a distance, right, between the Earth surface and the satellite. So you need to add that one. Okay, so you got wait, I'm using my calculator. See the answer is different. So let's see whether the answer the given is correct or not. Okay. So this one is if you add, you will got 6.37 0.37, okay, exponent 6 plus 4.22, okay, exponent 7. Okay, so you will get this one, right? 6.37 times 4 plus 4.22, 6.37 exponent 6 plus 4.22. Wait, where's the radius? 4.22 times exponent 7. Okay, so you got 448 for, let's change to the standard form. 1, 2, 3, 4, 5, 6, 7. So I take 4.86 times 10 power of 7. 1, 2, 3, 4, 5, 6, 7. So 4.86, right? 4.86 times 10 power of 7. So that's the R. This one, they ask you to calculate the, wait, let me see first. Oh, I'm sorry. This one is before it launched, right? So before it launched, okay, right. So this one is actually we calculate after that is launch, right? So I erase it first. Okay, so this one is before it been launched. So we have to take the R is the distance, the radius of the earth. Okay, so means we just multiply, okay, g m1 m2 plus r square. Okay, so 6.67 times 10 power of negative 11. The mass 5.97 times 10 power of 24. Okay, and then multiply with 1.2 times 10 power of 3. Okay, and then the R, we have to take the radius here, 6.37 times 10 power of 6. Okay, because before it launch, of course, it has to be at the surface of the earth, right? So we just take R, that one. Okay, so if you use that one, did you get the same answer? You got 202.56. Did you got 202.56 if you use this one? Okay, let me check. So 6.67 exponent negative 11, okay, multiplied by 5.97 exponent 24, and then you have to multiply with the mass of the satellite, 1.24 exponent 3. Okay, so you got this one, right? And then you must divide by the radius of the earth, 6.37 exponent 6. So you got this one. Is it correct? Can you calculate for me? Try to calculate for me, maybe. Oh, R square. Sorry. R square. I forgot to square the R. We calculate again. 0.97 exponent 24. Okay, times 1.2 exponent 3. Okay, you got the answer. Divide by 6.37 exponent 6. Okay, and square it. Right. So yes, you got like this. 1.11,776.13. Okay, so same answer like this one. Okay, you get 1.2. 1, 2, 3, 4. Oh, you round off, is it? Right, Shonki, if you want to give to the decimal point, the answer in the decimal point like that, the standard point, the standard form, please take until 2 or 3 decimal point. Okay, don't take 1, because if only 1 means the answer like 1.2. This one actually the answer is quite long, right? So it means you have to round off. Okay, so round off to the 2 decimal point. So 1.18, right? 1.18 times 10 power of negative 4. Okay, so this is the answer. So this one is actually before it being launched. So it's still on the surface of the earth. Okay, so this is the force. Okay, so the next one, you have to calculate, all right? After it being launched, okay? So this is before. Okay, so the next part is, oh, wait. So for the next part, you have to find the force, okay, after it being launched. Okay, so can you calculate? So that one you got 202.56. Is it? 202.56 is actually after it's being launched. Is it? Kayi Yilin, the one that give me the answer? Yes. Okay. So let's see whether it's correct or not. I'm using, okay. So we calculate first the distance, right? So the radius here and also the r and also the distance from the earth surface to the satellite. Okay, so r plus h. So now the formula will become like this. M1, M2, sorry, not this. Okay, G, M1, M2. Okay, so r square. Okay, but r plus h, right? R plus h square. Okay, so what is the r? R is actually the radius of the earth, and we add some more, okay, h. Okay, the satellite, the distance between the satellite to the earth's surface. So this is the formula for this question. Let's say if ask you what is the gravitational force after it being launched. Okay, so the G here is 6.67 times 10 power of negative 11. The mass of the earth is 5.97 times 10 power of 24. Okay, and then the mass of the satellite is 1.2 times 10 power of 3. Okay, and then the R here you have to add, right? The radius of the earth is 6.37 times 10 power of 6 plus 4.22. Oh my god, plus 4.22 times 10 power of 7. So we have to add the radius first. Okay, don't forget to square it. Okay, so let's find whether the answer is correct or not. So 6.37, okay, exponent 6, right, plus 4.22 exponent 7. Okay, I forgot to put the bracket. Yeah, we put 4.22 exponent 7. So we put the square. So you got like this 2.36 times 10 power of 15. Okay, so that is the radius. 2.36 times 10 power of 15. So this one I already square it. Okay, so the next part is you can calculate 6.67. Okay, 6.67 exponent negative 11. Okay, and then multiply by 5.97 exponent 24. Okay, and then the mass of the satellite is 1.2 times 1.2 exponent 3. Okay, and then you got the answer. Then you divide with 2.36, right, exponent 15. So is it same answer? Yeah, 2.202.47 Newton. Okay, so you can see the force, gravitational force is decreasing, right? Before this is it is 11,000, right? Now it only become like 200 something. Okay. All right, so we already answer this one. Okay, so we compare the mass. Okay, so the mass is of the sun is bigger than mass of the earth, right? And also the mass of the earth is bigger than the moon, and the moon is bigger than the satellite. Okay, so after that, we have to compare the Earth satellite distance and the Sun Earth distance. Okay, so if we compare, you can see the distance between the Sun Earth is larger, or is larger than the Earth satellite. Okay, if you compare the distance between these two. Okay, and so predict the difference in the magnitude of the gravitational force between man-made satellite and the gravitational force between the sun and the earth. Okay, since the sun has the highest mass, right, between these four, okay, and the distance of the earth sun is larger than the distance of the earth satellite. So we can conclude that the gravitational force between the sun and the earth is bigger. Okay, between the sun and the earth is bigger than the earth and the man-made satellite. Okay. Okay, the next part. Okay, this one we already calculate. Okay. This one we already discussed, right? So we don't need to discuss again. Okay, so the next part is you have to relate the before we continue, right? Do you have any question about the gravitational force, okay, between the sun and the earth, or between the uh, earth and the man-made satellite? Do you have any question you want to ask? Okay, maybe you don't want have to you are not sure how to use the formula of the gravitational law. Any other question you want to ask? No question. Okay, so we move on to the next part is the relate gravitational acceleration G on the surface of the earth, okay, with the universal gravitational constant G. Okay. So according to the Newton's second law, okay, that we already know that F is actually equals to ma. So this is a Newton's second law. And what is A? A is actually the acceleration, right? Okay, but let's say if you want to use it, let's say you want to find the force that acting on the object, okay? So we use the F is equals to mg. All right, G is what? G is the gravitational acceleration, okay? And also the unit also both is same, Newton, okay? So according to the Newton's second law of motion, gravitational force can be expressed as F is equals to mg. So from Newton's universal law of gravitation, okay, gravitational force is actually F is G m1 m2 divided by r squared. So what is the relationship between the G, right? The G and also the capital letter G is the gravitational constant, right? So what is the relationship between these both? Okay, so the first part is F is equals to mg. Okay, and also you have to know mg is actually is equals to weight, right? Weight is mg. Okay, so let's say the question asks you what's the meaning of the weight. So the gravitational force that acting on the object. Okay, so that's the meaning of the weight. So F is equals to mg, right? So F is also equals to g m over r squared. So, and then this one is equal. Okay, equal. So we can make equation like this. Mg is actually equals to plus r, plus divide by r squared. Okay, so we just can cut the m here. Okay, so it will be left g is equals to g m, all right, divide by r squared. Okay, so I explain again. So F is actually equals to mg, right? And the another that we already learned just now, F is g m1 m2 divided by r squared. So these two force is equal. So I can take that mg is actually g m1 m2 per r squared. So actually the mass here, okay, is the same object. So you can just cut. So it will be like this, Gm2 over r squared. Okay. So the relationship you can see here, okay, G is directly proportional to the capital letter G. So when the G is increased, this also will be increased, the gravitational constant. Okay. So what's the relationship between the gravitational acceleration G and the gravitational constant G? So this is the formula, right? The equation that we just get. Okay. So this is the relationship is directly proportional to G. Okay, what are the factors that influence the value of the gravitational acceleration? Okay, so the mass of an object and also the distance of an object. That one you can see from the formula here. Okay, so the mass and also the radius. Okay, or you can say the distance. Okay, gravitational acceleration always towards the center of the earth. Right, so each planet in this universe has its own different gravitational force. Okay, so the value of G is 10 ms negative 2 or Newton kg negative 1. So what does it mean by Newton kg negative 1? That means for 1 kg, okay, for 1 kg and for 1 kg of an object, there is a 1 Newton force that acting on it. Okay, so let's say 1 kg 1 Newton. So if you're 10 kg means the force that acting on you is 10 Newton. Sorry. Alright. Yeah, 10 kg 10 Newton. Okay. So let's say for the moon, right? So what's the gravitational acceleration for the moon? So moon is 1/6 from the gravitational force of the earth. So we know that the gravitational of the earth is 9.81, right? So 1/6 means 9.81 divided by 6. So you got like 1.5 something. Okay. So that is the gravitational acceleration of the moon. Okay, for this activity 5, okay, calculate the value of the gravitational acceleration for 5 distance. Okay. Okay, so let's say I'm giving you, this is the radius of R, right? 6.37 times 10 power of 6. Okay, so let's try to answer this one. Okay, so this is actually already been calculated for you. Okay, so R, so this is the distance R. Okay, so this is 2R. Okay, and this is 3R, and this is 4R, and this is 5R. Okay, so already calculated for you. You can see when at the R, okay, at the R, the gravitational acceleration is 9.8. Okay, then after is 2R means the radius is double now. Okay, it decreased become 2.45. Okay, so at 3R, okay, the gravitational acceleration reduced to 1.09. Okay, at 4R, 0.6125. Okay, at 5R, okay, so 0.392. Okay, so what we can conclude here? So when the distance increase, what happened to the gravitational acceleration? What happened to the gravitational acceleration? Decrease. Okay, so the gravitational acceleration decrease. Okay, so we calculate, right? We calculate already calculate the value of the gravitational acceleration. So you can see here, we can just plot a graph, right? So when we plot the graph from 0 to R, the gravitational acceleration will increase. Okay, so when it start from R to 5R, the gravitational acceleration is decreased. Okay, we already proved that one. Okay, by the calculation from using this calculation. So when we plot, okay, you can see that the first from the 0 to R, it's increasing. Okay, but after it pass the radius of the Earth, okay, after that you can see the graph is decreasing. The gravitational acceleration is decreasing. Okay. So what is the value of the gravitational acceleration on the Earth's surface? So the answer is 9.8. Okay, so plot a graph of G against R. So if you plot the graph, it will become like this. Okay, the one that you see in front. Okay, so graph shows the variance of the gravitational acceleration with the distance from the center of the Earth. Okay, so for this one, okay, at this part, we can say that G is directly proportional to R. Okay, because it's a straight line, right? And it's increasing. Okay, so G is directly proportional to the R. Okay, so at this part, okay, okay, G is equals to GM over R square. Alright, so this one means the G is 9.8. At this part, the value of G is 9.8. That means it's on the surface of the Earth. So let's say this is U. So that's this is the part. Okay, when the object is on the surface area, on the Earth's surface. So when it start leaving the Earth's surface, okay, the distance increasing, you can see the graph of the G, the value of the G also become decreasing. Okay, so more then if you travel further, more further than the Earth, it will keep decreasing. Okay, so that's why the graph look like this. So this one is actually when it's still on Earth. Okay, this one means it at outer space. Okay, so this one you have to remember. Okay, so how does the value of the gravitational acceleration change when the distance from the center of the Earth R is smaller than R? So you can see at this part, R is smaller than R, so this means at this part. R is smaller than R, it means at this part. So you can see it's directly proportional. Okay. So how does the value of the gravitational acceleration change when the distance from the center of the Earth increase? Okay, that means R is bigger or equal with R. So the value will be inversely proportional. Okay, because you already know the relationship of the graph. If the graph look like this, okay, it is inversely proportional. If the graph look like this, it is decreasing linearly. So this one is look like this, right? So means this one is inversely proportional. So for this part, directly proportional. For this part is a directly proportional. For this part is inversely proportional. Okay, for this part, G is directly proportional to R. Means when the radius is increasing, the gravitational acceleration also will be increased. Okay, but at this one, the at the top here, so at the top here, this one is actually G is 9.8. Okay, so means the object is on the surface of the Earth. Okay, and then when it start leaving the Earth, okay, so means the radius increasing. You can see when the radius increasing, the gravitational acceleration also will be decreasing. So this is inversely proportional. So are you clear? Anything you want to answer? You want to ask? Yeah. All right. So for this one, can you calculate for me using the formula F is G m1 m2 over r square? You are 3M, right? How many 3M and 3M comes today? What? 5 only. Then ask them to go to the lab. So later we just do the experiment that I told you yesterday. Okay.
Proxy, second floor. And class, can you please call them? Come to Mama, please. Okay? Faster. Right, wait here. We'll have it. Right.
9.81 ms -2. So this one we already proved that here at the top part of the graph here, the G is 9.81. Okay, so we already proved that one, okay, by this question. Okay, so yeah, 9.8 times 9.8 ms -2. Okay, a radar imaging satellite orbits around the Earth at height of 480 kilometer. What is the value, right, of the gravitational acceleration at the position of the satellite? Okay, so can you try to calculate this one? So this one, what formula that you need? So only use this one. G, okay, M over R square. Don't use this one. This one is actually for the force, for the gravitational force. Okay. Now we want to calculate the gravitational acceleration. So gravitational acceleration, we use the one that we already derived. So use this one. Okay.
Sorry, that's not.
Oh, it's okay. Okay, for our extra class, I will start after the cuti hari raya. Means like during our PDPR, right? During PDPR is on like usual, okay? And then on Saturday also we still have the class, okay? So on Saturday is actually I will not teach a new topic. It's actually to teach you how to answer the question, because I got a feedback from you, right? You said that you can understand in class, right? But later when I do the test, right, you cannot answer because you don't know what's the question one, right? You're not familiar. So on Saturday I will do the SPM question. Okay, so it will 8.49. Okay, 8.49. Others? 8.49. Okay, let's see. G is the gravitational 6.67 times 10 power of -11. Okay, and the mass is 65.97 times 10 power of 24. Okay, and then the radius is 6.37 times 10 power of 6. Okay, so if you calculate, right, is it correct? Yes. And then you have to add by 4.8. Okay, this one I changed to standard form. So 4 times 10 power of 3, right? So 1, 2. So 4.8 times 10 power of 5. Okay, square. So you got 8.49. Okay, good. Okay, discuss the condition where the value of the gravitational acceleration is almost zero. Okay, so microgravity is the condition in which people or object appear to be weightless. Okay, so the effect of the microgravity can be seen when astronaut and object floats in their spacecraft or spacewalk. Okay, so heavy object move around easily. So microgravity means the acceleration almost zero. The gravitational acceleration is almost zero. Okay, so you can see the video here, right? So they float. Okay, so this is the microgravity. Okay, so this one means the gravitational acceleration is almost zero. Okay, so before we move on to the next topic, okay, so we can conclude here. Alright, we already learned about Newton gravitational law. That is m1, m2, okay, and r square. Then you derive become g m1, m2, r square. Okay, we already know that force is directly proportional to the m1, m2. F is inversely proportional with r square. Okay, and then we got this equation. Okay, this one we can use to calculate the gravitational force. Okay, gravitational force. Okay, and then after that we already learned how to calculate g, the gravitational acceleration. Okay, so the formula is g m1 over r square. Okay, and you already learned the graph. Okay, so let's say this is r, right? Okay, so this is r. Let's say 2r, 3r like that, right? So from here to here it will be inversely proportional. Okay, so g at top here is g is 9.8, right? ms negative 1. Okay, this is actually when the object is at the earth. Okay, this is at the outer space. Okay, this is the outer space. All right, so here the gravitational acceleration here 9.8 is actually when the object is on the surface of the earth. So when it start leaving the earth, okay, so you have to use this, you have to see the graph. Okay, this part of graph. So the gravitational decreasing, right? And then we already learn to calculate the gravitational acceleration, okay, by using this formula. Okay, so next we have to justify the importance of the knowing the values of the gravitational acceleration of the planet in the solar system. Okay, so gravitational force is a universal force. So any planet they have their own gravitational force. Okay, so that is a new universal force. So the formula G equals to Gm over r square can be used to calculate a gravitational acceleration on the surface of other bodies such as planets, the moon, and the sun. Okay, so this formula is not using it's not using for the earth only. Okay, you can see you can use it on, let's say you want to calculate for the another planet. Okay, let's say for the Mars. Okay, for the Neptune, let's say. So other any kind of planet you can use this formula. Okay, so this one is actually the comparison. All right, the gravitational acceleration. Okay, the comparison between the earth, okay, sun, moon. Okay, so you can see the sun has the highest gravitational acceleration, that is 274. Okay, and the lowest one is actually the earth. Okay, 1.6. Okay, so this is the value of the G. So this one you don't need to memorize. Okay, just for your knowledge. Okay, this is for the Jupiter. Okay, Saturn, Uranus, Neptune, and also Pluto. But Pluto is actually not a planet. Okay, so actually only Neptune only. Pluto is already considered as not as a planet. All right. Okay, so which planet has the largest gravitational acceleration? Wait. Gravitational. Why? We can take the book on my table. For those is only come today. And also the money, is it? Oh, okay. Thank you. Okay, so the gravitational acceleration, which planet has the largest gravitational acceleration? So the planet is, for the planet is is Jupiter. Sun is not a planet, sun is a star, right? So that's not considered as a planet, even we know that they have the highest gravitational acceleration, but sun is a star, not a planet, so it's not counted. Okay, so it's a Jupiter, right? Which planet has the closest, right, to the gravitational acceleration on the Earth? Okay, so the answer is Saturn. So 9.8. Ours is 9.8, right? So let's see the Saturn. Saturn is 10.4. So that is the closest one. Okay, what factors determine the value of the gravitational force? Okay, this one, you just see the formula, right? So G is G is Gm1 over R square. So the mass and the radius. This is the factor that determine the value of the gravitational of the planet. Okay. So why gravitational acceleration of planet is important in space exploration? So this one is to keep the satellite in orbits. Okay. So it keeps the satellite in orbits, and gravity influence the path taken by the everything traveling through space. So they will not collide with each other. Okay, and we know that not only one satellite, okay, there's a lot of satellite. So this is to make sure that the satellite will not collide with each other. Okay, and then it slow down the spacecraft during landing. Okay. Alright, so importance of knowledge of gravitational acceleration of planets in continuity of life. So rain to fall. So if there is no gravitational acceleration, so the rain will not fall down. Rain to fall. Okay. And heat to dissipate. Okay. And another one is air and water to separate. Okay. And blood fluid flows. Okay, so this is the importance of the gravitational acceleration. Okay. So anything you want to ask? No. Okay. So wait. It's quite noisy here. Okay, describe the centripetal force in the motion of satellite and planet system. Okay, so this is the new topic that we're gonna learn. Okay, centripetal force in the motion of the satellite and the planets. Okay, diagram shows a four position of a satellite which orbits around the Earth at the uniform speed. Okay, so you have to observe the direction of the velocity of the satellite at each position. Okay, so the gravity will pull you towards the Earth. Okay, but the speed of the satellite will go in the straight line like this. Okay, so the gravity pull you is like a 90 degrees here, right? So the gravity will pull you to the Earth, and this is the speed here. Okay. Right. So centripetal force in the motion of satellite and planet. A body move in circular motion always experience change in direction of motion even though its speed is constant. So when you rotate, right, for this one, you see the direction is going upward. Okay, but when you follow the path here, you can see the direction change, right? Before this, the direction is going upward, and this one, the direction is already moved to the left. So means the direction always change, right? Always change. Okay, when it rotates, the direction is always change. Okay, but the speed is same. Okay, the speed is same. Only the direction is same. Only the direction is changed, but the speed is same. So that's why it's using the speed here. It's not using the velocity, because velocity is a vector, right? So vector means the scalar and the magnitude and the direction must be same. Let's say if put here velocity. So if put the velocity here means you already know the direction and the magnitude is same. But this one is said the speed is only same. Okay, means the direction will always change when it rotates. Okay, so let's say it move like anti-clockwise. Okay, so when it move anti-clockwise, you can see this one, the speed is the direction is going upward. Then we rotate at this side, the direction is already changed. It moved to the left. And then when it goes to at this side, the direction changed to downward. So the direction will always change. Okay, so only the speed is constant. So therefore, the velocity of the body change. So the velocity change because of what? Because of the direction is same. Sorry, the direction is changed. But the speed is constant because the value of the magnitude of the speed is same. So let's say the speed is 30 meter per second. So it rotates, alright? It rotates in 30 meter per second. It's not changing anything, okay? But the direction is changed. So means the speed is constant, the velocity is changing due to the direction of the rotation, okay? It's keep changing, all right? So a force is required to change the direction of the motion of body. Okay, so there must need the force to change the direction. So the force that change it, we call it as a centripetal force. Okay, the force that change the direction. Okay, because we know that the satellite will move in a circular motion, right? It will revolve around the Earth. So means the direction is changed. You will move like circle like that. So there must be a something that so they can change the direction. So they need the force. So that force we call it as a centripetal force. Okay. So force is required to change the direction of the motion of a body. So the force that act on the body which move in circular motion is called as a centripetal force. Okay, so you can see this is the video. See, it's rotate. Okay. So question number 1. When the rubber stopper make a circular motion, the stretched string exert a force on the rubber stopper. What is the direction of the force? So in the direction towards the center of the circle. So let's say okay, there's stick here. Okay, then there's a rope here. Okay, I tie it. Okay, and then it start to rotate. Okay. Alright, so this must be the force, right? So the force is the direction is toward the center of the circle. So when it rotates, okay, the F will move toward the center of the circle. So this force is known as a centripetal force. Okay. So what's the relationship between the speed of the rubber stopper and the centripetal force? So when the speed of the rubber stopper increase, the centripetal force is increased. So let's say you rotate it more faster. Okay, so when you rotate it more faster, okay, so you can see the centripetal force also will be increased. Okay, so will be increased. Okay. Okay, how does the centripetal force change when the rubber stopper make a circular motion with the smaller radius? So means the let's say the radius, okay, before is like this. So let's say this is the F. Okay, so this is the rotation. Alright, and we make it smaller. The radius is smaller. Okay, so let's say this is the object. This is the R. So you can see the R is smaller. So what will happen to the centripetal force here? So the centripetal force also will increase. So you can feel the increase of tension in the string. So the centripetal force is increased. So let's say what happened when there is no centripetal force. So if you rotate with no centripetal force, the object will move. Okay, let's say you cut the rope. So what happened to the object? The object will move straight line like this. Okay, because there is no centripetal force that acting on it that make it rotate in circular motion. Let's say you cut this rope. Okay, so let's say this is the stick. Okay, and then you tie it with the rope. Okay, this is the object. Okay, and then you start to rotate it. Okay, then after some time, let's say you cut the rope. So what will happen to the object here? It will move straight line. So this means that this is the one, the force that attract the ball so it can rotate on the it can rotate in circle like that. Okay, so this force we call it as a centripetal force. Okay, without it, the object will move with straight line. Okay, with the straight line, in the straight line like that. All right. Okay, a force acts on body in the direction toward the center of the circle for a body in circular motion. So this is the formula if you want to calculate the centripetal force. That is F is equals to mv square over r. Okay, so F is the centripetal force, m is the mass, right? The mass of the object that you rotate. V is the linear speed here. Okay, V is the linear speed here, and R is the radius of the circle. Alright, so centripetal force in motion of satellite and planet. So just now we only see, alright, the object. So what happened is actually with if satellites and planet. Okay, so linear speed V show how fast a body move in a circular motion. So give three factors that affect the centripetal force. So you just see the formula mv square. So m is the mass, v is the linear speed, and r is the radius of circle. So let's say the question asks you what's the three factors affect, so you just refer back to the formula. Okay, mass for object, linear speed, and also the radius. Okay, so example 1. Can you try to calculate first? For example 1. Okay, what formula should you use? Mv square over r, right? 160. Others, 160. Always the same person that answer the question. Others very quiet. Why you not just try to answer? Okay. Actually, I consider this one also as your PPD. So because the chat is also being recorded, right? So I have a proof for those who always answer my question. So this will help you a lot, okay, in your PPD. (1,600) sums got 160. Okay, so let's see. So the answer should be 1,600. How come you get 160? The notes not clear, or it means the diagram for the radius and the mass. Radius, oh, okay. This is 1.8. All right. Okay. Okay. Can a satellite orbit the Earth without being driven by a rocket engine? Okay. So prediction of Isaac Newton that a satellite can orbit around the Earth without being driven by the rocket engine. Okay, so this is a prediction of Isaac Newton. So object launch with a low linear speed will follow trajectory 1 and reach the Earth at Q. Okay, so low linear speed. Okay, so let's say you launch the satellite with the low speed. Okay, it will follow the trajectory 1 and reach the Earth at Q. Okay, so object launched with sufficiently high linear speed will follow trajectory 2 circulating the earth. So the object will not return to the earth. So mean if you want to make sure that the object is rotate, okay, is rotate, all right, means it will not fall down to the earth. Okay, so mean you have to use a certain speed. Okay, you have to use a certain speed so it can rotate, okay, around the earth. So let's say if you use a low one, it will come back to the earth. Okay, so if an object speed launch with a low linear speed, it will follow trajectory and reach the earth. So this is the prediction of Isaac Newton. Okay, so this is actually the experiment that he used. Okay, so this is called as a Newton's cannon. Okay, so initial speed, you can see the value of the initial speed here. Okay, so it's keep increasing until now it's increasing to 8,000 meter per second. So when it launch at 8,000 meter per second, okay, it will rotate. Okay, so let's see first. Let's see again. Okay, 4,900. Okay, so it still keep come back to the earth. Okay, and then it's increasing 5,900. Same is still come back to the earth. Okay, and then 8,000. Okay, so it launch and will not come back to the earth, so it will keep rotate. So it needs a certain speed. So if the object launch with a sufficiently high linear speed, it will follow trajectory circulating the earth. So this is by using the Newton's cannon. So this is actually the experiment. Okay, prediction of Isaac Newton. The prediction of Newton is now a reality with so many man-made satellites orbiting around the earth without being driven by any thrust. So it's not driven by any thrust. So they can rotate, all right? They can orbiting around the earth. Okay, but means they need a certain speed. So that's why when they want to launch a rocket or something, they have to calculate whether the rocket can reach the certain speed, because they know if the rocket cannot reach the certain speed, okay, it will come back to the earth. Okay, so that's why they will calculate first. Okay, what is the speed that the rocket can achieve, because before it being launched, right? So they need to have a certain value. They already calculate the mass or on, okay, and then they say, okay, whether this rocket can reach this certain speed, then it can orbiting the earth. Okay, so that's the reason why they need to calculate first. Okay, so satellite always experience gravitational force acting towards the center of the earth. So the gravitational force on the satellite act as a centripetal force. It's same also. Okay, because they say this is earth, this is the man-made satellite. Okay, so it's still orbiting. So you already know the force that there is a force, the gravitational force, right, that attract the earth to the satellite, and so the satellite to the earth also, they have the same gravitational force. So the gravitational force is actually acting as a centripetal force. Okay, so that's make the keep rotate, okay, around the earth. Okay, so anything you want to ask teacher about the centripetal force, okay, about the gravitational acceleration? Anything you want to ask before I stop? No question. Okay, so later I will assign a quiz, right, for this one. Okay, so let's see whether you really understand or not. Okay, and I hope you already take the notes. Okay, you already take the notes at the canteen, because that one you paid. Okay, you paid, so please take. Okay, so see you on. Alright, so I think we are gonna see each other again until after Hari Raya, after cuti Hari Raya, right? Because Monday already school holiday. Okay, so take care. Alright, so see you after cuti Hari Raya. Okay, for the new PDPR. Okay, so thank you class. All right. So if any question, you can text me. All right. So thank you. Bye. Bye. Selamat Raya. Thank you. Bye.